Number one here, we're looking at complete photoelectron spectroscopies, as it says here in number one. Now, the only trick to doing these, and I don't for the love of everything know why they do this, but sometimes when you look at the problems, they have the big number over to the left and the small number over to the right. Seems silly, seems backwards. There must be some reason for it. I honestly don't know what it is. But I wish I could tell you that every time that you are going to be given one of these, that's the case. So your brain could begin to get used to that. But sometimes that's not true. So here in problem number one, you see the big number is on the left and the small number is on the right. But if we go to number two, in number two, the big number is on the right. So here's the big number, and the small number, the 0, is over here to the left-hand side. And not only that, but they have it split in tiered situations, where from here to here it is 0 to 10, but from here to here it is 10 to 100, and then from here to here it is 100 to 500. So the first thing that you have to do when you do one of these problems is to decide which way are they giving you the information. Are they giving it to you normal way, where small is to the left and big is to the right, or are they giving it to you the backwards way, where big is to the left and small is to the right? In this particular problem, it's a backwards one. Now, why does it matter? Well, if we're removing electrons, like we saw in the ionization energy, remember you always remove from outside in, and the outside ones are easier to remove than the inside ones, and so the outside ones are always the small ones. So what you're going to want to do is you're going to want to find the small ones, and that's the outside valence ones. So for example, in this example, the answer turns out to be sulfur. We'll get to that in a second. But you've got the inner shell, you've got the second shell, and then you've got the outer shell. Remember that the outer shell is always the easiest. So if the small is over here, the outer shell is going to be the easiest. The inner shell is always going to be the hardest. So when you go to look at an electron configuration, remember that you always start in the order of 1s and then 2s and then 2p, and remember the maximum you can put in the 1s is 2. Here they are, 1 and 2. And the maximum that you can put in the 2s is 2. Here they are, right there, 1 and 2. Numbers 3 and 4 here, boom and boom, right? So 1 and then 2 there. And the maximum you could put in the p subshell is 6. Here they are, p1, 2, 3, 4, 5, and 6. Right along the way. So I always find it easiest to start with the big numbers, knowing that the big numbers are actually going to be the ones that are on the inside of the electron notation. The big numbers are always your 1s's, because they are the closest to the nucleus, and because they are the closest to the nucleus, they are the hardest to remove. So consequently, knowing that big is over here, this is going to be your 1s, and you'll notice over here you've got little dashes, 1, 2, 3, 4, 5, and 6, like so, and you can tell that this guy here is in the 2 zone here, like so. So this is going to be 1s2. So that's the first ones that are there. And then this next peak coming over, that's going to be level 2, except that level 2 is split into the 2s and the 2p. So this guy here is going to be your 2s2, and this guy here is going to be your 2p6, because again, if we count up to the top here, then this guy here is going to be your 6. 1, 2, 3, 4, 5, and 6th zone up there. Then our next one, after 1s2 and 2s2 and 2p6, we have reached this point here. Now we got to go more, so that takes us down to this level. So that's going to be your 3s, as it says here, 3s 1 and 2, which clearly we have here. So that's going to be 3s2. And then finally, our next ones that are here are in the 3p zone. So again, this is your third energy level, first, second, third. So this is going to be your 3p, and apparently we get up to 4 here for this guy. And so 3p4, 1, 2, 3, 4, which is why this guy is sulfur. So this guy is 3p4. You'll get used to these the more you do them, but the basic idea here is to simply start at the big numbers, find the big numbers, and then follow the electron spectroscopic notation configurations for the electrons until you run out. So this is simply going to be 1s2, 2s2, 2p6, 3s2, and then again this guy gets up to number 4 here, 1, 2, 3, and 4. So that's 3p4. So you come down to 3p4, and that is sulfur. So once again, your first energy level here that's closest to the nucleus, that's going to be your hardest electrons to remove. Then your second energy level here, there are 8 of them. That's going to be the next hardest to remove, the first easiest to remove, I guess. And so that's your 8 here, right? 2 and 6 is your 8. And then finally, your valence shell here is the easiest to remove, and there are 6 in the valence shell. There are 6 in the third shell, and that 6 is here. 3s2 and 3p4 get us our